Hey, welcome everybody to DEFCON 1 Science, episode number 2 with Landon, Curt, Noll. You guys remember Landon? He's the smart guy, also known as the mathematician, computer scientist, astronomer, and all these other titles that we tend to give him. But tonight, guess what we have for you? We have actually Landon going to give a presentation on some of the hottest things on Earth, which are nuclear weapons. Actually, to be specific, thermonuclear weapons, which... I have a little bit of knowledge of, not much, but obviously I work in the nuclear field, so hopefully we kind of conjoin my knowledge, his knowledge, and make sense enough for you all to understand how a nuclear weapon works. You're not going to learn how to build one. Sorry. But anyways, Landon, my friend, welcome back.
Well, thank you, and good morning, good afternoon, or good evening, depending upon your time zone and latitude. Good morning, from your friendly secular astronomer.
And if it's a flat Earth, then it doesn't matter. We're all in the same time zone, right? So
exactly. So this is a topic that I've given talks on before, and in fact, the last time I gave a talk was in Antarctica. It was shortly after I had a phone call. I called Steve, and we had that conversation.
He called me from literally the South Pole from an Iridium satellite.
Yeah, standing on the site. But as I didn't have the presentation there. It was later on, and I'm known to go down there and have invited talks to warm people up. And the previous talk was on the Kilauea volcano eruption, and then this talk I decided to give on the proliferation issues relating to nuclear weapons.
And just to let you know, in the middle here, you can see it where we have two windows here. I'm on twice. He's on twice. Twice. I am having a speech impediment today.
More than once.
More than once. Yeah, twice more than once. You know what? I really picked a bad day to stop drinking. Maybe I should have some alcohol this morning. Is it that early? No, it's not. Never too early for a beer. But I'm out of beer, so.
Well, he's got
Merlot.
Yes.
Yeah, I did. After last night, you know what? I had like one drink, and that was my limit for the week. But anyways, I know we have us in the middle here, but that's okay. Because what it's going to be is he's going to have the presentation in the middle, and then I'm going to make it larger for you all to see it. Because I have not seen this presentation yet, which may be good, maybe bad. I'm kind of going in blind. I have no idea what it's going to entail. So, you know what?
Keep the bleep up going, but you're going to dig in my presentation.
This could go horribly wrong. And by the way, I saw what Fred did in the live chat. He says, this show should be rad. I saw what you did there. Okay, I saw what you did. I get it. Well done. Bravo.
Well, by the way, notice a shrink-off radiation that's surrounding...
Chenyakov radiation.
Yeah.
Chenyakov radiation is blue, but yeah, I guess it would work.
Yeah. Well, it is kind of slightly green, but usually it's a little bit bluer there. You got to fix that.
Yeah. And can somebody in the live chat tell us what Chenyinka radiation is? We'll give you a brownie point if you can. Okay, so you want to just dive right into this and start your presentation?
Yeah.
The way we're going to do this, guys, if you want to ask questions, we'll take some in the middle if they're kind of basic. But if there's anything like more complicated, then we're going to wait to the end because we have a lot of slides to get through. But, you know, during the middle, if there's something about the science that you're not getting, ask us. We'll try to throw it out there and kind of explain as we go. But Landon, go ahead. Let's start. Just dive right into it. Do your presentation.
All right. Let's do the share here, and then I'll flow up this thing and do a play. And I assume you can see this now.
I can see it, and I am showing it to the outside feed as well, and they can see it still too.
So here we are. Some of the hottest things on Earth's nuclear weapons, and we're going to be focusing on issues regarding anti-proliferation of atomic and thermonuclear weapons. And this is actually would be part of a much larger course if you were doing it, perhaps even potentially a graduate school course. But we're going to try to condense it down to a short period of time. So it's just sort of skimming over the major parts of this. So I guess one of the first things you talk about is that, are we allowed to talk about this? Yes, we can talk about nuclear weapons. It's important to understand all the information that's in this talk has been obtained from public sources. And where physics and reality disagrees, we'll use the public information. There's some key aspects of nuclear weapons that are omitted from this talk. Simply, some data is glossed over due to lack of time. Some critical data is omitted because it's not really necessary. I mean, this is not how to build a nuclear weapon. This is what are nuclear weapons, so that we can talk about how they're made from at a national level and issues about non-proliferation. So again, no classified information is used in this talk there.
Which, by the way, as people may know, we did have security clearance at one time. There's nothing that I have in my brain that's kind of be considered classified, except for maybe some specific numbers, which we have no use for in this particular presentation anyways. So even if I wanted to divulge any kind of classified things, I wouldn't have the ability to do so. So ain't got to worry about me.
Yeah. And I used to work for an unspecified branch of the federal government, and I also did an internship with a guy named Teller. But we'll have some Teller stories.
Just some guy named Teller.
So let's say, well, the next question is, okay, we can talk about nuclear weapons, right? It's not, and again, we're not going to be doing classified stuff. We're going to talk about the general topic. The next question is why? Why would you want to talk about nuclear weapons? One of the things I think in particular is that because nuclear weapons use in your lifetime is probable, right? Those that are alive today will probably see or experience a case of a nuclear weapon being used, unfortunately. So this thing will get you more informed if it happens and have less panic. Be informed about non-proliferation issues. What's easy, what's hard. So when you hear people debating about things like Iran or things, issues like North Korea or those sorts of things, you have at least some more context in there. Now, it's also interesting physics too, at least for a physicist. And so there's a little bit of that involved. The other thing I think is also really important is help diffuse the fear of non-weapon nuclear. There's a tendency for people, when they hear about nuclear power, or even something as simple as nuclear medicine or nuclear batteries, something like that, to think weapons, right? This is a very, very different set of topics, and I'm trying to help diffuse that. So we're going to talk about how bombs work, some of the basics on there. We're going to talk about nuclear materials, and we're going to talk about the hard parts. What's hard? What is there? And so this is the generalized agenda. And by the way, for those that are listening, I might have it in slides as I put pictures up that sometimes are vaguely related to the topic. So if you get bored with listening to me, you can figure out why there's a fish there in the agenda basket.
Looks more like a dead cat.
It is actually a fish.
Oh, I can see and,
it's actually, and it was a photograph taken in Anchorage, Alaska. So atoms. First, we have to talk about atoms. Atoms generally you see these sort of pictures here. Can you see the cursor, by the way? Is that?
No, I can't see the cursor.
Okay. Well, you can see sort of atoms. That sort of atomic symbol is kind of the ubiquitous sort of items there. But atoms have two sort of main zones. There's electrons, these negatively charged things on the outside, and there's a nucleus in the center that's positively and neutral charge. The atomic nucleus. Okay.
That'd be more of the Bohr's model, by the way, right?
Yeah. And so this is not to scale, but.
It's not even accurate, but
yes. But it's pictorial, right? And so the atomic nucleus has these protons that are positively charged and neutrons that are neutral, and it's rather small. I mean, typically the size might be between we talk about femtometers. That's going to be 1,000th of a millionth of a meter, between them, about 1.75 and 15 centimeters in size.
There's neurons in the atomic nucleus.
Whoops. Thank you for that. See, I can even go back to here. Neutron.
There we go.
Thank you.
No, still not.
Thank you.
You're getting close. Still not right yet. There we go. We'll get it. We're making it.
Neutrons. There we go. Yeah. Neutron. Thank you. All right.
People thought it funny. It was like they were like not to scale. They were like, yeah, it's not to scale. Go figure, right?
Yeah. So the thing is about one of the things that is critical to understand is that most of the mass is in a tiny volume. 99.95% of the mass of an atom is in the nucleus. I mean, protons have almost 2,000 times the mass of an electron, and most of the atom is empty space. So atom's volume is typically a trillion order of more than a trillion times the volume of the nucleus.
And the interesting part is even inside a nucleon, like a proton or neutron, that's 99% empty space as well. So what does matter then if it's all just empty space? The inside of the nucleons are empty space because they're just basically quarks that are in there that are popping in and out of existence. And the orbitals are considerably just some distance from the nucleus. So matter is almost pretty much nothing for the most part.
And so look at the scale. You can see the scale where there's, I have a bar at the bottom, 100,000 centimeters in size of hydrogen atom, and the actual nucleus is 1 femtometer. So if you took a hydrogen atom and scaled it up to the size of a ping pong ball, or the nucleus, right, the proton in a hydrogen atom, and scaled it up to the size of a ping pong ball, the electron would be over 400 meters, or about 1,300 feet in size. Right, that gives you just an idea about just how much nothing there is within nucleus. And remember, 99.9% of the in an atom is mostly nothing, and that 99.95% or more of the mass is in that little tiny small section. Now, another thing to understand is that while you have the periodic table and you talk about chemical properties, you have things called isotopes. They're the same type of element, but they have different number of neutrons in their nucleus, and those change the nuclear properties as well as the mass of the atom in question. And in nuclear, so if isotopes become quite critical, they're essentially not of relatively little interest in classical chemistry, but in nuclear processes, they're actually quite critical. There are a few interesting isotopes for nuclear weapons. You have typically two, and certainly with others, but most of the time you're dealing with two types of uranium, 235, 238, plutonium, 239. There's three types of hydrogen, 1, 2, and 3. Beryllium, helium, and lithium come into play typically as well. And there's other ones that show up, but mostly that's what the interesting isotopes for nuclear weapons. Nuclear fission is splitting the atom. Certain large atoms are rather unstable, and particularly when they say absorb a neutron, they begin to oscillate violently to the point where they will split. And when they split, you have two positively chunks now that have they're very, very close to each other. Remember, the nucleons are very small, so you have two pieces that are highly positively charged, very, very close to each other. Think of like two magnets that are repelling each other at close distance, and they fly apart at great enormous things. It happens very quickly. So the oscillation and splitting of an atom happens in about 10 billionths of a second. What they call a shake of a lamb's tail is the expression the nuclear people use. And typically splitting, like for example, U-235, when it absorbs a neutron, turns into U-236, which is unstable, and within 10 millionths of a second, it splits usually into two chunks, few times into three chunks. Usually when the two chunking things, they're kind of in a 2 to 3 ratio. And also, in addition to those two chunks, you typically get about 2 to 3 neutrons flying out. It also produces some gamma rays or hard X-rays, very, very energetic light that comes from the fission. So one of the things again to understand is, well, why is nuclear fission so energetic? Why are nuclear bombs so energetic? Why are nuclear power plants such a dense energy source relative to chemical? Well, again, the two pieces that typically when an atom splits are positively charged at very, very close proximity to each other, and so they will fly apart at enormous velocities. And that repulsion and flying apart is essentially the punch of one of the big punches of nuclear power. Chemical actions involve the electrons on the outside of the atom, and while you can get obviously energetic chemical explosions, the chemical processes are dragged down by the mass of the internal nucleus. Remember, 99.95% or more of the mass is inside the tiny nucleus of the atom. So chemical actions are dragging around this nucleus, and so they're not as energetic, nearly as energetic as you can have with nuclear.
And it should be noted that the vast majority of the energy released is actually due to the kinetic energy of these fission fragments. People think that when things will break into two, when a fission will take place, that the energy being released is some kind of mystical force that comes out of it. No, the energy is actually kinetic energy, because these things are going to be vibrating afterwards. There's going to be this kinetic energy moving back and forth really fast, and that's going to produce heat. That's where the heat comes from these chain reactions.
Yeah.
Although there's some gamma, obviously. There's gamma rays produced as well. But. Yeah.
And there's some neutrons, but most of it comes from those pieces flying apart on the fission. And it's a compact energy source. I mean, if you look at a 1 billion watt coal plant, would need about 80 train cars of coal per day to operate. Whereas if a 1 billion watt nuclear plant, you'd need about a half train car of nuclear fuel per year. You need, it's almost 1/15,000th the mass for a 1 billion watt nuclear plant than a coal plant. And as I say, Steve's went to a very, very technical school on learning how to operate these kind of facilities. Can tell you lots of stuff. We've had, I guess, discussion online about nuclear plants on there, but.
Yeah, the cores that I worked on were only 150 megawatt reactors, so they're a little bit smaller design. I mean, the core itself is actually not much bigger than your average sized trash can. But people kind of noting in the live chat about the strong nuclear force. Maybe we can just talk real quick. Why is it that the energy released is energy that comes from splitting the atom? Why is there actually the stored energy in there? Where does that stored energy come from?
I mean, certainly there is a strong nuclear for the binding force, because one of the things, why doesn't a nucleus fly apart? And things, for example, in things like helium atom, got 2 protons and 2 neutrons in close proximity to each other. It's the strong nuclear force that keeps those together.
Yeah, the strong nuclear force is the force that holds the nucleon together itself. The strong nuclear force is the gluons holding the quarks together. But there's a secondary effect that because the strong nuclear force is so strong but so limited in range, that it actually goes beyond just a little bit the range of the radius of the nucleons, and that's what overcomes the electrostatic repulsion of the protons themselves. So, because you got protons and neutrons together, protons are plus, they're going to want to go away from each other, but the strong nuclear force, the secondary effect of the strong nuclear force is great enough to prevent that from happening. That's why if you take the individual neutrons and protons and you weigh them, they weigh differently than when they are binded together in a bound state in a nucleon.
Because there's binding energy there.
That's what's
that
called
binding energy.
Yes, exactly.
And the old E equals mc squared. The energy of that binding energy has effectively an equivalent mass. Now, when you split an atom, like let's say an atom like U236 splits, the two pieces separate, and now the strong nuclear force is binding the two pieces. But you have the repulsion, the positive charge, electrostatic repulsion is going to act on them, because the binding within the nucleus is a very short range phenomenon. And even but the splitting and finding of two atoms next to each other, the nuclear force can't recombine them together, but the repulsion from the positive charges produces an enormous amount of energy from the kinetic kick that they give. Much like you have two magnets that are close to each other, repelling each other.
We don't see that in the macro world, right? If you take two basketballs and two bowling balls and they represent neutrons and protons and you put them together, it's not going to change the weight of them. I mean, if you weigh them individually and you weigh them together, it doesn't change. But in the microscopic level, it makes a huge difference when you're working with neutrons and protons. And that mass defect, because of E equals mc squared, then that's the energy that's being released,
Sure.
And that's what's going into the fission fragments, and that's what's going into the gamma rays. And the 2.3 neutrons or 2.4 neutrons are going to be released afterwards. That's going to have energy as well. So all that total energy, that's where it comes from, is that mass defect.
Yeah. But in the case of splitting the atom, like uranium, most of the energy you can harvest comes from essentially the repulsion of the two fragments. So some of it comes from the neutrons being kicked out. Some of it comes from the gamma rays being that come out of it, but most of it is that kinetic kick. Now there's chain reactions, because one of the things I mentioned is that when U235 absorbs a neutron, becomes U236, within 10 billionth of a second, it splits. Let's say typically in something like proton and barium. Typically the two pieces will fly apart kinetically, but it also will send out between 2 to 3 neutrons. Those 2 to 3 neutrons, if you have the right conditions, are capable of finding other U235 atoms, which will absorb that neutron, and they'll split again and again and again. So this condition of splitting creates what we call a chain reaction. Now you need a lot of chain reactions to get a significant amount of energy. I mean, while it's 200, what they call it 200 million electron volts of energy, that's essentially the equivalent of potential energy of 200 million, volt potential across there. You need about 31 billion reactions for a joule. That is, if you want 1 watt for 1 second, you're going to need 31 billion splits to get that. So 31 billion splits will be enough energy to lift an average tomato 1 meter, or 3 feet. So if you want to power a 100-watt bulb, you're going to need 3.1 trillion atom splits per second. But atoms are small, so you don't need a lot of mass. I mean, we're talking about something, almost a trillionth of a gram per second to power a 100-watt light bulb. And again, that's one of the things why nuclear plants are very, very compact power sources compared with chemical plants.
Yeah, what's called energy density is something along the lines of, if you have a certain amount of material like uranium and you have a certain amount of gasoline, you're going to have more bang for your buck because there's a higher energy density for uranium than there is for an equal amount of some other material. So you can have very small amounts of uranium and get you a very large amount of energy release as opposed to some other sources of fuel.
Sure. So moving on here, there's something called critical mass. And critical mass is the smallest amount of material needed to have sustained chain reaction. Remember, when you get when you split an atom and it sends out those 2 to 3 neutrons, you want at least one or more than one to find another atom and have those atoms split. So we have something, there's something called the bare sphere critical mass. How much stuff do you need to put together into a sphere in order to get a chain reaction going? Because if it's too small, the the neutrons that come out of reactions, many of them leave the material flat in space and don't do anything. If it's big enough, however, there's a reasonable chance that more than one of those neutrons coming out of a split will find other atoms, and the chain reaction will go.
Basically, the definition of criticality is that for every one neutron produced, a fission event takes place. So basically, it's a 1-to-1. That's what it means to be self-sustaining or critical.
And so nuclear power operators are taught how to keep that at 1.
Mm-hmm. But you do go supercritical every so often, by the way. A common misconception when you're starting up a reactor plant, you do actually reach a supercriticality position, and then you go beyond that, then you're going to do a criticality. So when you hear these words like the reactor went critical, or even the reactor went supercritical, it's nothing to be afraid of. I mean, those are normal courses of action is when you're starting up a reactor plant.
Yeah. So anyway, this barosphere critical mass says how much material would you need to put into normal density in a sphere. And for uranium-235, you would need about 52 kilograms. And it's 17 centimeter or a 7-inch diameter chunk of U-235.
Now that would be under normal conditions, non-compressed, right? That would be if you just...
Normal density.
Normal density, okay.
Yeah, you're not trying to boost anything. Plutonium, you need a lot less. It's about 10 kilograms, about a little less than 10 centimeter or a little less than 4-inch ball of plutonium-239. If you brought that together in just packed it with your hands, you would get you'd get a chain reaction. So and again, these chain reactions have exponential growth. So one neutron splits, and let's say it emits 2 neutrons. Those 2 neutrons find more atoms. You get 4, 8, 16, and on up. So you can get this exponential growth. Remember, each of these stages, each of the generations occurs at about 10 billionth of a second. So if you had a perfect 2x chain reaction, so you had material that was supercritical that allowed a doubling growth each generation, you need about 87 generations for U-235 and 85 generations for plutonium-239. And in something less than a millionth of a second, you will have had a complete chain reaction of lots of material, and you would release an enormous amount of energy, up to about 100 kilotons of energy, and things would go boom, right? So but this it's not simply a matter of stacking stuff together, as we'll see. It's not a simple stuff. First of all, you can't have material sitting in supercritical form. In part because there's always neutrons found in the natural background. And even if you were somehow shield all those stray neutrons in the natural background, there are also a few unstable atoms that will spontaneously fission. So a critical sphere of unstable atoms will actually blow itself apart. This is the case, a Godiva experiment where they were seeing, trying to bring together U-235 and slowly increasing its mass, and the mechanical apparatus had a malfunction, and sort of it blew itself apart and damaged it. But again, you just can't simply just stack a bunch of stuff together and then have it go boom. Even if you could, there would be a spontaneous fission that would set it off. So that's not the way to...
Yeah, you've got to be really careful of these types of nuclear incidences. I mean, these types of criticality events that they're called have gotten people killed.
Yes. With
demon core and things of other things. There's plutonium, but these are highly. The word isn't volatile, but they're highly susceptible to criticality, and so if you don't have them in the proper geometric position, and they do get too close to each other, they can be, for the very reasons that Landon explained, due to spontaneous fission or to neutrons from other sources, can lead to a supercriticality event.
Yeah.
So a lot of energy released very quickly. You will die.
And so if you want to have a nuclear stockpile, you can't have a bunch of critical or supercritical piles sitting around, because they'll go boom on you, right? You want them to not go boom while you have them, right? That's generally the idea. And again, you can't simply drop enough material into a pile. So let's say, okay, you're gonna be clever, and you're gonna have half critical down here and half critical down there, and you'll just go thunk, right? Because it's uranium's dense, goes bang. The problem is that stray neutrons will start the reaction. The reaction will create enormous forces, and it will blow itself apart. You'll get an explosion. Any people that are nearby within direct shot will get lethal dose of radiation. You won't get the boom, but like a nuclear weapon, you'll get a fizzle. So again, you just can't simply drop some stuff together. It's not like someone brings together and get something. You do not want barosphere critical stuff sitting around, or even material even close to a barosphere critical type of material, because if you get the wrong configuration, things will go haywire, right? It won't explode like a nuclear bomb, in part because when the reactions start going, when you have those generations, those 10 billionths of a second doublings, it doesn't take them very long before get enough energy density that thing will blow itself apart.
Yeah, you can get a partial explosion, you can get a complete fizzle. There's a lot of different things going to happen, but you're not going to get the most bang for your buck because your efficiency went to hell.
Yes. So one of the things to do is, and people that are involved with weapon designs, is they look at changing the point of criticality. That is, how can you change critical conditions? And one of the things you can do is you can add more fuel, right? Adding more fuel until it goes critical, but that tends to be a bit of a problem. Besides, fuel is very expensive. You can change the shape of it. So when you see pictures, let's say of U-235 or plutonium, you won't see spheres typically. You'll see maybe flat pancakes. Why? Because the reactions, if they're stray neutrons and stray splitting, most of the neutrons that come out of that split will go to either side and not hit a critical atom. So one way you can change the criticality of stuff is to round it, change it more in shape. Another thing you can also do is cool it. Hot fuel is less reactive than cold fuel. So cooling is another method. Another is to change the density, crush it, right? You can squeeze the thing down, because when it's squeezed, the atoms are more tighter together, and those neutrons coming from those fissions will have a greater chance of hitting something at a shorter distance. So you could have a subcritical sphere, and if you crush it, you can make it go critical because of the density. Another thing you can do is actually do a neutron reflector. You can reflect neutrons back in. So the neutrons that escape outside of your material can be reflected back in, so that you can also increase. And for example, beryllium or U-238 shells are examples of neutron reflectors. Now, some key problems in making a bomb is you got to collect enough chain. In fact, I see another typo here. Chain, not chain reactable, chain reactable. Reactable. There we go.
Yeah, and it should be noted that all the things that he said when it comes to the helping of maintain a supercriticality state or uncontrollable exponential chain reaction, all those things are incorporated. Compression, reflection, these all are things that go into making a actual nuclear weapon.
Yeah. Also, when you're talking about a power plant, all right?
Same thing for a nuclear power plant as well.
The distribution of material.
You don't want to like implode the reactor core.
No, but you in fact build reactor cores so it can't do that, right?
Well, yeah, it's physically impossible. The fuel itself in the reactor core is actually going to be in pellets, or it's going to be in these round spherical things that have a niobium coating around them. They're very small, but they're just not in any kind of geometric shape that you can ever get that kind of uncontrollable criticality from that alone. Now, you can have a reactor obviously go supercritical, but it's not going to blow up like a bomb. It's going to heat up really fast.
Yeah.
It's going to cause a flashover of the pressurized water, and that's going to blow up the pressurizer, or even the vessel. But that's a steam explosion, not a nuclear one.
Yeah, and again, it's no secret. You can't take a nuclear sub, hit it with a torpedo, and have it chain reaction go boom. It's not like a powder keg where you have an old ship with a bunch of gunpowder and you throw a hot shot into it and the whole ship goes boom, right? A nuclear powered submarine, neither the nuclear power generator nor the weapons are in form that will go boom unless very special things are done to them. In the case of the reactor, it's basically impossible. In the case of the weapons, it requires a thing to be done in order for them to go boom. So, key problem with making a bomb is you've got to collect enough chain reacting material. You've got to make the super, super chain conditions, right? So you've got to have conditions where you'll have a chain reaction that will minimize the loss of neutrons. You've got to keep it together long enough, between, about 0.85 microseconds or more. And you got to keep it together in extreme conditions for those final few reaction checks. Remember, most of the energy on a bomb comes from the last couple of generations, right? The last generation gives you half of its energy. The second to last generation gives you a quarter of the energy. Third reaction gives you an eighth of energy. So you have, 7/8 of energy come from the last 3/10 billionths of a second. So you got to keep it, but leading up to that are pressures and temperatures that are just unbelievably difficult. So you've got to keep it long enough, and you got to hold it for those last few 10 billionths of a second in order to get any kind of yield. And those last 2 billion seconds, you have material under enormous temperature and pressure. It's not an easy thing. So it's not just a matter of putting a stick of dynamite together and lighting a fuse. One of the problems is that chain reactions blows itself apart. So if you go and bring two subcritical pieces together, before they even get close to each other, again, spontaneous fission will cause reactions start to occur. You'll get supercritical events near the surface, the two surfaces. They will become, you get enormous amount of energy in there, and they'll basically blow the two pieces apart. And again, you'll get a fissile. So you need to be able to create critical mass conditions quickly enough, and they need to sustain for long enough in order to get any kind of yield other than fissile. So the basic design, one of the simple designs of an atomic bomb, the simplest type is called the gun type bomb. You basically slam two critical chunks together, right? You have an explosive charge that takes two subcritical pieces and slams them together and hold them together. Enough momentum helps make them supercritical. You surround them with a tamper so they will reflect neutrons back in and make it go critical. In fact, the very first gun type bomb, was the very first nuclear bomb that was designed was a gun type bomb. Now they're highly inefficient, right? So the typical, the first one this was the Batman that was dropped on Hiroshima, and you can see the dimensions over there. It was highly inefficient, but it used U-235, and by the way, you build a plutonium gun type bomb. Plutonium chain reacts too fast, and it would fly apart much faster. So you need highly enriched uranium, and you need a lot of it. The thing that is important to understand, we're talking about nuclear proliferation, is you do not need weapons-grade uranium in order to make a bomb with any kind of yield. Even, Hiroshima bomb that was probably 15% efficient still had a major amount of destructive force. The type of enrichment that was done for the Hiroshima bomb was about 79% enriched uranium. Right, this is not considered weapons grade.
I thought it was 80. I thought it was 80, but not, 1%. But isn't it 80?
It's actually 79. It's actually a little bit under 79. But part of the thing is that we've learned more about what are the maximum yields in recent years by both.
Yeah, you don't need, like you pointed out, you don't need that kind of enrichment for commercial use.
Yes. So this is well beyond commercial use, but it's less than what's called weapons-grade uranium, and that's an important thing to understand. The device was fairly simple. You had two chunks of U-235. That was 79% U-235, and so those are those two red things there. And the orange thing is a powder keg. Basically, this was a cannon to launch the outer rings, slam them into the inner rings. Surrounding the inner rings at the bottom was a lot of U-238 that act as a reflector to reflect the neutrons back in. And so the things slammed together with a reflector. It creates a density, went supercritical, and then went bang. And that's what Little Boy was. The Hiroshima bomb was never pre-tested. So you hear a lot about the Manhattan Project and people like the people like Oppenheimer and people like Feynman, doing work out at Trinity site. The actual first bomb that was designed was by a professor as grad student, even before the Manhattan Project had been started. Right, it was designed there, and they were so confident of that they didn't even pre-test it. Right, and so when the Hiroshima bomb was dropped, it was not the product of the Manhattan Project. It was a product of the grad student and professor, and no one was really surprised that it worked. On the other hand, the thing that they were concerned about was whether or not the Trinity experiment could be repeated. And so the thought was, well, U.S. really had ability to do one of these gun-type bombs, because again, it took a lot of highly enriched uranium to do this, and U.S. was unlikely to be able to have many of these types of bombs. So if the plutonium bomb had not worked or had fizzled, they'd at least have one of these shots. But again, the gun-type bombs are relatively easy to build. And again, they had so much confidence that they didn't even pre-test it. They just dropped it and said, okay, it works. Now, gun-type versus implosion, because we don't use gun-type bombs. They're easy to build, easy to design, simple to explode, but they're also extremely dangerous in storage. I mean, if that powder keg goes off and those two pieces slam together, it blows up in your face. Even in the case of when the airplane that took it to Hiroshima, the bomb, the powder keg actually set up in the cockpit. And during the flight, one of the jobs of one of the people is to take that powder keg, go back into the back of the plane, down into the pit, and insert the powder keg into it. Much like the old gunships wouldn't necessarily put powder kegs in all of their cannons all the time. They would arm them when they were getting ready for battle. Right, this same sort of thing. They're dangerous to store. It also requires, the other thing of the gun type bombs is requires lots of hard to purify U-235. This is not reactor type grade. This is actually more enriched, certainly highly enriched, not necessarily weapons grade, but it needs a lot of material on there. Implosion types are they're safer to store. They require less material, and then they also can use plutonium. They're also technically more difficult.
And they're more efficient.
Yes. And that's why you need less material. And you don't have to use U-235. You can use plutonium.
And I do believe, and I could be wrong on this, but I think I'm not, though. The ones that use plutonium are less susceptible to long-term storage decay, because uranium weapons tend over a specific amount of time not to work after a certain amount of time. There's just not enough material left to still cause criticality. But with the plutonium weapons, you can store them longer and still be viable.
Now, one of the difficulties with storing weapons material is that it is still radioactive. It's transforming, and the crystalline structure begins to be bothered. I think that's one reason why, for example, in nuclear power plants, you typically use small pellets. You would not use large chunks, large sheets, even if they were subcritical, because structurally it becomes quite problematic.
And also, you want to use smaller things. You get a more even distribution across the core, right? Because you're going to have a neutron flux density that's horizontal across the core. If you just took a section of it, and as you raise the rods, you're exposing more fuel to the neutron flux density. And the thing is, if you don't have an even wear, you're going to get some of the fuel rods to be higher than the other ones. You want it to wear evenly, so you want this even distribution. Yeah. So these pellets, and there are actually pellets that are in these zircon oxide.
Zirconium
oxide layers, and that is wedged to get them in a plate that is inside there. And so that mixture causes a more uniform distribution, so you have more even fuel utilization.
Yeah. So implosion-type bombs are, again, much more efficient than gun types. You can use plutonium, right? So high enriched uranium also works, but high enriched uranium is more of a pain to design. But implosion-type bombs are more complex to design and build, and they require a complex explosion. And I mean by complex, I mean a complex explosion. It's not simply a matter that you just go and apply a bunch of dynamite around some uranium and all of a sudden it goes bang, right? You have a very, very complex explosion type on shockwave with things called explosive lenses. And it requires sub-millisecond timing of detonations, and those detonations have to be uniform. This explosion is not simply pack enough, C4 to have it go boom. It has to be a very precise thing. In fact, some explosions are too rapid, and some explosions are too variable. So explosives are too variable. So you have to have the right type of explosives. You need to have people who really, really know what they're doing. And this is an area where it becomes highly classified, and it is also technically non-trivial. So the first nuclear test, not the first bomb that was dropped in Hiroshima, but the first nuclear test was an implosion-type bomb. Again, because they knew that they could do the Hiroshima-type, gun-type bomb. They knew a high degree of confidence it would work, but they also knew that it was very inefficient and it would require lots of nuclear fuel that would be very difficult to build many of these bombs. So the first nuclear test was an implosion-type bomb, Trinity test, and the yield was around, now the yield is estimated better now at about 22.1 kilotons. That is 22.1 thousand tons of TNT equivalent explosion, plus or minus about 2.7 kilotons. And the way this system works, whoops, go back here, let's go back again. For here is that you have, it required, the Trinity explosion required 6.1 kilograms of plutonium. That's less than, that's not the barosphere, right? It was subcritical amount compared to like 52 kilograms in the gun type bomb. And so you had only 41% of the barosphere mass. So the Trinity device had only 41% of the material necessary to spontaneously go boom. So what they did was to have this sphere of explosives. They had fast and slow explosive with a lens that created a shock wave, a very uniform shock wave, which crushed the material down into the center before it then reacted, went critical, and went boom.
Yeah, I like this diagram because it actually shows the pressure wave that's actually doing the compressing in the middle from the actual explosion itself.
And so you're trying to squeeze this core in a very uniform, precise way, and you're trying to do it with you're not trying to blow the hell out of the thing, you're trying to squeeze it and hold it. And that's a very different thing than just saying blow it up, right? And yet, this was only about 22% efficient. But again, and somewhere about only about 20% of the material underwent fission. The other 80% of plutonium was just scattered. It still needed sub-millisecond timing detonation, which for the 40s was a very difficult thing to do, and for today, it's still a difficult thing to do if you do not have the so that the timing is difficult. And the other thing to remember is those explosives that are all around that sphere have to be very uniform. You can't have one a little bit more charged, the other that punches through, otherwise it squirts out the other side. You got to have a very, very uniform explosion, very, very uniform shock wave. and it is difficult. So since the Trinity, that's the Los Alamos device that was tested, and then the subsequent device that was dropped, the second nuclear bomb that was dropped on Nagasaki was a plutonium device, a number of advancements have occurred. One of the things is that they've come up with much more elaborate types of dual speed explosives of fast and slow. So the typical thing is you have fast explosives that will build a shock wave that will then detonate slow explosives that will hammer the inside. And the second thing that's done is called the levitated pit, that there's a gap, that you don't put the explosions right up next to the critical material, you have a gap. Now you think about, it's called the hammer effect, right? If you're going to take a hammer, if you place the hammer at the head of a nail and push hard, you'll get the hammer into the wood. But instead, to be more effective, you take the hammer back and you get some momentum and you strike it, right? You want that build of that momentum before you get the impact. The same thing they found, the levitated pit around the nuclear material is actually quite critical, pun intended, for giving you more effect. So one of the things they found is, again, the last chain stages gives you most of the power. And so the ability to hold in and reflect in those last few 10 billionths of a second is critical to boost the yield from the 20% up towards close to 100%. So an example they use is aluminum and beryllium pusher around a 238 temperature. So uranium-238, nice and dense material. Aluminum beryllium will reflect neutrons, and U-238 around it will give you some momentum for a hammer. So it's different between a tiny hammer and a giant sledge. But again, you have a pit, you have the elevated pit, you have an air gap, you have this really dense uranium-238 big giant hammer, and underneath it you have aluminum beryllium that's going to reflect the neutrons back in to make them more efficient. So this tamper pusher is one of the things that's been, they've improved over the training types design. Another thing is inside. Typically, one of the things that they started doing was using polonium-beryllium neutron emitter. Sure, you could wait for, when you squeeze this thing, you could wait for a spontaneous fission or stray neutron to start the reaction. But they found that they could seed it on the inside where you have beryllium being exposed to an alpha decay process. So polonium emits alpha particles. If an alpha particle strikes beryllium, it splits into 2 helium atoms plus 2 neutrons. So this beryllium polonium mix is a nice neutron emitter, right? And in fact, if you were to be fool enough to buy some polonium and put it next to beryllium, you'd all of a sudden start to get a shower of neutrons coming out, because it's a fairly effective, and produces fast neutrons. Now, those fast neutrons are not necessarily the type of thing you want to boost the weapon. I'll talk about how those are used, but those emitters, there's stuff you can do to take those fast neutrons, either slow them down or do something else to increase the yield. But we're talking now about ability to have inside the core, inside the bottom of it, a neutron emitter. So now what you really have is a shell, right? You have an air gap between your uranium sledgehammer with the beryllium aluminum reflector hitting the shell, which inside at the very center with another pit is this natural sort of neutron emitter. So you get neutrons in the inside so your reaction starts on the inside, not somewhere on the outside, and it can be more efficient.
And it might be noted that most of North Korea's weapons are probably, I would suspect, a boosted type of weapon like this rather than a true full-on fusion weapon, because they say that they have fusion capability now, nuclear weapons that are based on fusion. But it's probably
we'll talk about that to see about what they might have done. But yes, the first types were actually relatively simple things. And polonium, beryllium is a really simple thing. Now, there is an advanced technology called neutron guns. There are, as you say, electronic devices that use an accelerator that bombarding deuterium, tritium material, metal hydride target that will create neutrons. And these kind of neutron guns can generate neutrons on demand. So you could now have a situation, rather than have this radioactive neutron on the core, which you really don't want it efficiently generating neutrons, you now have this electronic device where you can inject neutrons into the center on demand using things called neutrons.
Less chance for accidents probably too that way.
Yes, yes. And so modern devices typically have gone from the fuse, right, just like a cannon having the slow match, to a neutron gun for safety purposes. They can also do some other things as well, but it's primarily a safety device. Another improvement over the design is to getting rid of the requirement for spherical shockwaves. The folks, the way they did it in Trinity was the best way they knew how at the time with explosives, but people become much more clever about explosives. And one of the things that they do is to have the timing is hard to achieve, and with lots of explosives, it's hard to control even the speed and explosive force of all those items. So they come up with a linear explosion where you have essentially two detonators, where the detonators have on either side. You have a lining that sort of deforms it, and the explosion basically leaks around the outside. You have a pit which is not spherical, but it's been squashed. But the explosion is going to take those two plates and squish the oblong sphere into your critical shape. So now you only have to have timing of two things, and you can have those two things be. It's relatively easier to get two explosive devices being uniform, and you can have a non-spherical pit, so it's even safer, right? So there's even less. You need even less material because you can have it in even much less subcritical form.
So as long as they're detonated at the same time and you have a spherical shape being produced at some point, that's when it's going to reach supercriticality.
Yes, yes. And you might guess there's other things involved in this sort of thing. And again, this is where you leave the nuclear devices into classified design about this. But that's one of the things that they do is you will see in modern nuclear weapons, you'll see less of the shell type stuff you saw at Trinity. And even this hollow 2-point thing has been with a hammer effect. You need a smaller tamper, so you don't need an additional pusher like you have with the Trinity type devices. This, by the way, is a leaked was a diagram leaked by the Swedish nuclears of Sweden. Stepped right up to and then pulled back on detonating a thermonuclear bomb. But Sweden decided not to join the nuclear club and essentially dismantle the program. Unfortunately, they did such a good job of dismantling it and turning it off that they packed stuff away in documents, and then someone cleaning out some files essentially threw stuff out in the trash, and people found it, and some of the stuff actually ended up in the Soviet Union. The Soviets learned some unfortunate secrets that boosted their capabilities. This is one of those diagrams that was leaked.
Did you ever hear about that truck driver that literally designed and built, it wasn't a functional one, but a nuclear weapon, and he was just a truck driver, but he knew enough about it to actually get it, how a nuclear bomb would work, and it built one, although it wouldn't actually work because of he didn't have the material, but the theory was correct. A truck driver. Yeah.
And that sort of thing. That's the part of the thing is that this material, some of the stuff of how to do it is known, but the ability to do it is on the other hand very difficult to do, right? So you can have the concept and the model of a device, but actually making the material and successfully testing is a much more difficult thing. Unfortunately, we have to come to this man, A.Q. Khan. This man is a son of a bitch. He's alive today in Pakistan, and he black marketed centrifuge technology, black marketed a number of other technologies that we won't talk about that allowed countries like, in addition to Pakistan, Libya, Iran, North Korea, Iraq, etc., to begin to develop nuclear weapons. I mean, this, and sadly, it's the most likely scenario of a nuclear weapon being used in your lifetime will be as a result of this man. And this man, that sadly, the deaths of the people will probably be because of this person. He's an evil son of a bitch who has made the world far, 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 far more dangerous.
Yeah, matter of fact, the way that uranium is enriched, that process is just as classified as some of the nuclear weapon stuff, because they don't want these countries to be able to have the technology to get the centrifuges to enrich it to weapon grades specifications. So that technology is classified as well.
Yeah. So unfortunately, this person had access to some very critical information. Not only did he help Pakistan develop their nuclear weapon, but he did turn around and enriched himself on the side and gave some very, very, very critical information about it. Now, we know that this guy did it, in part because of Muammar Gaddafi. Muammar Gaddafi, Libya, decided at some point, hey, he decided that going nuclear and having nuclear weapons was not what he wanted to do, and that he could get back, quote unquote, into the graces of some of the Western nations by essentially dismantling his nuclear program. And so Gaddafi turned over to International Atomic Energy Commission his stuff, right? And in his stuff included notes from this guy with his fingerprints and his DNA all over it. I mean, they caught him red-handed. Now, he's under house arrest, unquote, unquote, living a very wealthy life in Pakistan. But again, I want you to remember this guy's name, because when the bomb goes off and you hear the horror stories, you're very likely to lay the deaths at the feet of this evil son of a bitch. Okay, now, let's look at one of the consequences. One of the consequences was Kim Jong-un, right? They sold his stuff, right? And now they know, because at that point, eventually the fellow countries leaned on Pakistan to arrest this guy. And while the president commuted his death sentence, they know a lot more about what he did. And one of them was to give this design to North Korea. So how did North Korea, and so North Korea started with a late 1940 technology. We know where it came from. We know the test yields. You look at this device here, this sphere, and this is a Trinity-style device, right? And you have, in fact, there's a lot of details there. You see the background, the missile that, quote unquote, might deliver, but this particular thing was too heavy for that missile to do. You even see that the on the side next to Kim Jong-un, that little portal, and that's the portal for a neutron gun, and a number of other devices. I'm not sure whether the North Koreans understood how much information, but just based on these couple of pictures and also the shockwaves of their yields, we know a great deal about, we know where his technology came from, and we know the design, we know the yield, we know a lot about what's inside there, even if the North Koreans
So we can actually analyze the type of explosion, the waves that are produced, the PES waves and things of that nature,
yes,
those types of things.
And shape this up.
Right.
We also can look at the isotopes that come out of it, and we also know the technology that Khan sold them to in order to get that. There's been
kind of like a signature, right? A fingerprint.
Yes.
Yeah.
Yes. Signature or a fingerprint or a style, right? There's also been cases where you might have heard a couple of times where all of a sudden, there's this, North Korean ship that's surrounded by, let's say, someone's navy, and North Korea gets all huffy and they surround the ship, and essentially the ship decides, this nice fishing trawler decides to go back to North Korea, right? Some of those ships may have been containing stuff that we don't want them to do, because one of the worries is not just maybe North Korea is not insane enough to drop a bomb on somebody, maybe, that's debatable, but they might be insane enough to sell it to somebody else who is suicidal to do this sort of thing, right?
Yeah, that's the dangerous thing, right? I mean, information is dangerous, because if this technology is in the wrong hands, there are people out there that may not care. And it just
because again, you know, in the talk, there's been some stuff that's glossed over. You know, people at Con did is it actually enabled them to build this device, and that device could be put into a fishing trawler, brought into a harbor, and tragedy can occur. You don't need to have a long-range nuclear missile to cause it to occur. On the other hand, we know the style of stuff, and should there be an explosion, we can look at the fallout and actually even identify the reactor for which the stuff came from. This has been explained to the North Koreans. You know, presumably it's by the Chinese, who said, you know, if we detect that there's a bomb in some other spot that comes from your reactor, you guys are toast. I mean, it's been explained to North Korea.
They're held responsible.
Yes, they're being held responsible. Anyway, so he started with, this is his first device, and again, they didn't, I guess, I don't know if they realized or they did realize how much information they gave away, but we knew what was going on here. They have gone since the 1950s technology for lighter and more efficient devices that we've seen pictures of. It is now believed that that North Korea now has likely thermonuclear capability. And part of it comes from this picture, part of it comes from one of their last tests. We'll go into that in more detail, but we need to talk about thermonuclear weapons in order for you to understand this occurred. The first time we gave this talk, North Koreans were at this stage, and we had a discussion about what would a North Korean thermonuclear device look like, and we very accurately predicted this shape at this stage, and we'll see more about what this is about in just a moment. Again, I want to emphasize that, you know, there is, you know, North Korea is a very serious situation where where even you guys are talking about, you know, war with nuclear North Korea as an option. You also have the capability of North Korea to sell devices or technology to other people, even if they don't want to get their hands dirty on things. So we have a serious situation, again, tracing back to Con. So let's talk about fusion for a little bit. Fusion is when you have merger of two or more nuclei. For lighter nuclei, the merged mass is lighter. So if you take, you know, two deuterium atoms and bring them together, they're forming helium atom is less mass than the sum of the two masses. The difference is binding energy. And this mass, this binding energy difference, is turned into energy. So when you fuse lighter material, you get more energy out. When you fuse heavy material, you get less energy, but lighter material fuses well.
Generally, I think the cutoff is iron 56.
Iron, yes.
Yeah, iron 56. Right. Anything higher than 56, you'll get energy. If you split it apart, anything lower, you'll get energy. You have to put energy into the system first, but then you get more energy out.
Yes, whether it's endothermic or exothermic.
Right.
So deuterium-tritium fusion is one of the easiest types of fusion to occur. You get lots of kinetic energy from the mass loss. It's a nice exothermic reaction. More energy comes out than goes in. Again, by taking hydrogen 2 and hydrogen 3, fusing them together and creating a helium atom with another neutron. Fusion needs energy to overcome the charges. Again, just like, you know, just like you get lots of energy when you split an atom, you need energy to overcome the atom. And actually, one of the things you also get is you need to have a small enough separation so that the two particles quantum tunnel into each other. right? The normal method of just having a high temperature would require extraordinarily high temperatures in even something like the sun wouldn't really work without quantum mechanics. That these two positive charged particles will jump into each other and
so you need to overcome the Coulomb barrier there, and tunneling effect helps to do that.
Yes, and so stars do this, and quantum mechanics is also deep in the level of what's going on with these kind of reactions. Stars, are about the mass of our sun, have this hydrogen, the cyclist hydrogen fuses to form hydrogen-2. The hydrogen-2 fuses together to form helium-3. Helium-3 fuses together to form more hydrogen and helium, right? And so you get this kind of chain. It's one of the common things where the sun's core at around 14 million Kelvin is doing this. And these nucleons fuse by quantum tunneling. You have a dense enough material inside, high enough temperature, high enough density, that these charged particles can get close to each other, and then the quantum tunnel allows them to jump and merge. The resulting has less mass, so it kicks out neutrino. Antineutrino kicks out gamma, and it also kicks out neutrons or protons depending on the reaction. So back to this sort of thing. One of the things that's happened with atomic weapons is they're now fusion boosted fission weapons. So you remember we had so what they do is they have a hollow pit, and inside there they have a 50-50 mix of tritium and deuterium. And it's not for thermonuclear, but rather to supply extra neutrons. So one of the things you could have is its ability of these extra neutrons will cause multiple chain reactions. So you need less plutonium to get the thing started. You can sort of get a jump or a head start on those chains going forward. So if you have something where you could cause this deuterium tritium to fuse rapidly, you'll get a burst of neutrons and a jump on those generations. You don't need to hold the material together. You actually don't need as much material in order to get things going and started. So a lot of modern weapons use a small amount of fusion at their core to boost them. We have seen that in the yields with what North Korea has done, and so in watching the North Korean events, the things that we've seen disturbingly are the boosting of efficiency from just getting it to go bang to getting it to go bang with efficiency. Why? Because either North Korea can build more bombs with less material, or they can more easily launch them on rockets to do nasty things. But we also can see the signature that say, yes, this is not merely a quote uranium plutonium weapon. This is a boosted weapon, and we can tell that by the yields.
Yeah, and it should also note that it probably will make up for losses of neutrons. Neutrons can escape. They can have various things that happen to them. They have leakage, which is what it's called, or resin escape probability, depending on what you're talking about. But the extra neutrons here help replace those neutrons that are lost. Correct? Yes.
And so again, you have around there, So now see that red ring is your plutonium-239 ring. That's your material that can go critical with a beryllium camp around the outside edge. You have shock wave explosion with a hammer effect, and you have deuterium tritium in the center that's going to give you a burst of neutrons to get the reaction going quickly. So fusion boosted weapons have an advantage. The pit does not need to stay critical very long. And so the massive U-238 tamper can be replaced by a very lightweight beryllium neutron reflector. You can cut the yield in half. Basically, you can get the same amount of yield with about half the mass. Or another way you can say is you can tune your explosion. Right. So if you want a particular explosion of a particular type, you just don't have to make a trinity. You can actually dial your explosion device depending on what it is you're trying to achieve. So nuclear miniaturization is another thing that's been in effect. Not just smaller, but reducing the internal commitment time. But boosted weapons also give you a reduced yield for smaller effects and require less material. The picture you see on the side there on the right is actually unfortunate. Actually, it comes from the UK, where they were doing basically an ad, right, to try to attract people to go in the Special National Forces, and it was not really realized that what they were showing you was a nuclear tipped propelled rocket. And if you look at, for example, in 1945 tech, where you have, I think that's in inches, a 60-inch diameter thing. There you have a 11-inch diameter thing, which later on they said the yield was about 6 kilotons. But this was kind of an unfortunate thing of saying, yes, here's the current state of miniaturization from 1945 to 1961. And that requires some of these techniques of boosting and so forth. Those things are easier to smuggle, harder to detect. There's less material. It's harder to even see the material if it's outside the device. And so these miniaturized things are much more susceptible to smuggling and proliferation problems. Unfortunately,
that almost looks. Is that a Davy Crockett? Because that looks like a Davy Crockett nuclear weapon.
No comment.
You can't say where I
don't think it's too useful. I don't know which are Davy Crockett, but it's that.
Davy Crockett is a M28. It's actually a rocket propelled RPG. Only the RPG is a nuclear weapon. They're about 5 to 10 kiloton.
It's probably it's sort of that class. Yeah. I don't know exactly.
Yeah. They call them Davy Crockett's. They were the smallest one that the U.S. arsenal ever produced.
But it was one of those bonehead things that someone said, what were you thinking when you reduced this sort of thing?
Yeah, the outside chest, the tactical nuclear weapons they were referred to.
Yeah. So thermonuclear weapons are staged, and usually you do it in 2 stages, right? And essentially you have a primary, the thing at the top would be your classical, and I'm using a diagram of a classical implosion type atom bomb, with a second stage, this thing down at the bottom, that reddish, dark colored object is your second stage. And the following stages are imploded by the previous stages. A staged nuclear weapon. You can go more stages. You can go to 3 stages or more. In fact, the Soviet Union tested a 3-stage device that was in the 50 to 100 megaton range, and there really isn't there isn't really a practical limit to the number of stages. It's just insane beyond 2 stages.
Well, the Tsar bomb, is that a 3-stage?
Yeah. That was very likely a 3-stage thing. The Soviet Union didn't really admit it, and Russia sort of said, claimed that they were the only ones that do a 3-stage device, and 3 stages are going to be more yield. So people say the Tsar bomb was the 3-stage device. Is the logic there?
That one only had half the yield it could have done too, from what I understand. That was designed to be 100 megatons, and it was about 49, I think, or something like that. So considerably less than it could have been designed for. And that was a hell of an explosion.
Yes.
If that bomb was dropped in L.A., I'd be dead.
Yeah.
I would be happy at least.
So
and I'm 2 hours away from L.A.
The main thing that's gone beyond sort of the boosted atomic weapons that are more efficient and 2-point stuff is now what's called the Teller-Ulam configuration, right? And Ulam sort of conceived some of the basic parts of it. Edward Teller added some important physics principles, and actually Enrico Fermi did the hard math on that. And believe me, the mathematics around this sort of stuff is pretty hair-raising, right? This is not trivial stuff. When you're starting dealing with quantum mechanics and fusion effects and so forth, it's a non-trivial piece of technology. But effectively, the primary is a classical atomic weapon, and the secondary is typically a thing where you have lithium deuteride. Your thing is going to fuse with a plutonium spark plug in the center and a reflective casing on the outside, filled with polystyrene foam. In fact, a lot of thermonuclear weapons are filled with polystyrene foam. And the reason for that is that polystyrene foam is going to turn into a plasma when the primary atomic bomb detonates, and that plasma is going to do some things. The secondary we'll talk about in just a moment. So in this thing, that's the stages. Before firing, you have essentially the foam encased secondary, the primary sitting on top, and so the next stage, you have the high explosive fires on the primary. So you're crushing the material, making it supercritical, and you can add all the stuff about neutron gun boosting and hammer effects and the levitated pit and the boosted center, but essentially you fire off your atomic explosives. The thing begins to go, turn in. You get the fireball, and one of the things it does is it irradiates the polystyrene foam. Polystyrene foam turns into plasma. The plasma compresses the secondary, and the neutrons trigger even more material as it goes forward. Now, by the way, I'm talking about lithium as this hydrogen, this lithium deuteride. The very first thermonuclear explosions were first thermonuclear device was actually using cryogenic hydrogen, cryogenic tritium. But that turned out to be an unyielding thing. So we're using lithium, and I'll explain in just a moment. But another important part of this process is this tamper pusher ablation. So before firing, you have stage 1. And in stage 2, the primary explosion's fired, the pit is compressed. Stage 3, the fission reaction completes. So it's gone to do its critical stuff. It primary is now at millions of degrees, generating hard gamma and X-rays. And it begins to heat the polystyrene foam, which is going to create a plasma, which begins to compress the thing. You have a block on top, which is going to start to push. You have materials that's in the center, plutonium in the center, which is also reacting. So the blue core is being squeezed from the outside, and it's being hammered from the inside from an atomic explosion, and the thing goes critical. If you think about the effects that are going on here, if you talk about the pressure, the radiation pressure from you're talking about towards the trillions of pascals, right? The radiation pressure that comes from the atomic explosion, maybe around 140 trillion pascals. The plasma from the foam around it that's being radiated gives about 750. But the ablation, which is this large block and it's being pushed down, is going to give you most of your pressure. And pressure is going to infusion is going to yield, right? You have to have the material that's going to fuse at a high dense temperature pressure in order for the nucleons to get close enough to quantum tunnel together and fuse and release the fusion energy. So modern thermonuclear weapons, and by the way, and you notice I'm not using the word hydrogen bomb, right? It's really not, nuclear weapons are not, it's kind of a misnomer. The reason why I call them thermonuclear weapons is it really is a fission, fusion, fission, fusion, fission process. Right, you know that. The primary starts fission. What's that? Well, that might be like the beryllium, which is being hit alpha decay and splitting, which gives you neutrons to take deuterium tritium center to fuse, which will give neutrons to the primary atom bomb to boost its yield. It goes bang. It produces neutrons, which crushes the material to generate fusion. That fusion is going to generate lots of neutrons, which will allow other material like U-238 undergo fission. Because yes, U-238 can split, right? But
it doesn't absorb them as easily as U-235. 235 presents a bigger target, what's called a macroscopic, or depending on if you're talking about overall, microscopic cross-section for absorption or macroscopic cross-section for absorption. So uranium-235, if you look at it and you look at the neutron is going to see it as a much bigger target area. It's called a Barn ratio, and than it will for the 238. So basically, imagine shooting at a small building and shooting at a big building, even though there's a size differential. The 235 and the 238, one appears to be a more efficient target than the other one, so it's going to absorb neutrons easier than the other one.
Yeah, and if you have a lot of fast neutrons, which fusion gives you, you can cause U-238 to split, but it needs a high fast neutron, not a slow neutron.
It needs a thermalized. Well, there's which one? What'd you say?
That you need the fast neutrons, right?
For 238.
Yes.
238. 238 tends to have fast neutrons over thermalized neutrons, but 235 it has a better chance to absorb a thermalized neutron or a slower neutron.
Yeah. So one of the things that probably is a misnomer is the reason why they don't call them hydrogen bombs. It's really a misnomer. About half the energy comes from fusion process and half comes from a fission process. And another thing to know is that while a fusion plant could be relatively free of high-level nuclear waste, fusion bombs still produce lots of waste and fallout, right? A fusion bomb, in fact, there's no, quote, known way to do a fusion-only weapon.
Yeah, because you need temperatures to get up there to initiate the fusion. And
you need a star.
You need something really hot. Well, I mean, why couldn't you do it theoretically with using X-ray type lasers or something?
I mean, it's difficult. Now, if fusion was really easy to do, we would probably also have fusion power plants, right?
Well, yeah. Well, we do. I mean, we've had fusion for quite some time. It's just not commercially available. They suspect the first one may come online around 2025. But wasn't it MIT? They had one working for like a couple decades.
But it's been the tokamaks. Things like tokamaks, and that's one of the things I worked on was doing computer work for the magnetic fusion energy people. And one of the things that the tokamaks could get to near critical or close critical for a very, very short period of time before the thing would pop itself out of the magnetic bubble, right? We don't have to date a fusion reactor device that can achieve even a break-even energy at this point. We are now getting to the point where we have fusion devices that actually begin to fuse, right? So that's happening, but we don't have a fusion power plant. So I guess if I were to use Steve your terms, we've gotten it to flash critical, but then it goes subcritical.
Yeah, the reason it doesn't stay at criticality, you have two things going on. One, I think the ones you're talking about, they still use what's called a Z-pinch technique, if I'm not mistaken, that will constrict the magnetic field such that you have a very small, high energy, high temperature conditions that initiate fusion. But once that happens, you kind of break down the magnetic field, and it just, as you said, spurts out, and it just causes the whole thing to shut down. Because you have in order to have a true fusion reaction where you have a higher output than input, you need to have that magnetic field sustained, and that's very difficult to do because of the fact that once you hit fusion, that magnetic field is no longer stable.
The math for the magnetic fields and fusion things is extraordinarily difficult. It is just. Yeah, it is very, very difficult.
Yeah, so, it's all tensor mathematics. I mean, there's tensor fields. They threw me at that problems for a while. It was a very, very, very difficult thing just to get your head around it. So, but what I'm saying is that if we were able to build, if it was easy to build, trivial to build fusion power plants, we'd probably know a lot more and might have the technology to build fusion-only weapons, but today there's no known way to do fusion. I think they might have the. You know what? I mean, I would go on a limb and say they if they really had to build one, they probably could have, but it wouldn't be efficient because it would be massive.
Yeah,
it'd be really massive to do,
and be complex and so forth. So modern thermonuclear weapons are a fission, like beryllium split, to boost fusion, deuterium tritium center, to generate neutrons to fission the critical core of the atomic weapon that's being crushed to generate neutrons to create ablation and radiation pressure to do fusion, which will generate fast neutrons to do fission. So it's this fission, fusion, fission, fission, fusion. That's why we call them thermonuclear weapons, not hydrogen bombs. So let's look at Kim Jong-un's thing. The assumption of what's happening here is that at the tip is your classical atomic style weapon. Now, one of the things that we note is this thing is considerably smaller than the first device that they had. And in fact, we've been seeing pictures of them that they're getting smaller and smaller, which means that they're able to get either better yields or use less material, which is, again, a worrying prospect. And that thing on the other side, the thing that's sort of in the center, is considered the second stage of the Telluride device. And so that's assuming that what we see inside there is the materials necessary to undergo thermonuclear fusion. Now, it's believed that some of the first device and that they detonated that was above 100 kilotons is likely was a very inefficient thermonuclear detonation. So there are some things that they're not getting right or not getting very efficient. The tragedy, of course, is when we see the analysis, the consensus is that, yes, they are getting into the realm of thermonuclear weapons. They may not be the big ones yet, but the other thing we've noticed is that their yields are getting away from them. And that, for example, the mountain they were using to do these devices inside is getting so structurally unsound that they're having to go and find another place to do their testing, assuming they're going to do testing, right? And it's kind of anyone's guess as to whether or not the agreement is going to be held or not. But the kind of consensus from the outside is this is an attempt to design a thermonuclear weapon by North Korea. Whether or not that works, or it may be even highly efficient, they're in the program.
This would be a demo then, right? Basically.
Yes. Obviously. Yes, a demo type thing, and it's possible that what they've done, given their yields, is they have certainly made a boosted atomic weapon, which is getting additional yield by a somewhat inefficient thermonuclear reaction of a Coulomb second stage.
Gotcha.
Now, I've been I went to Anahuac. The primary reason we went to Anahuac was to see a very wonderful total solar eclipse, the longest in the century. And it was courtesy of the Google folks that took me there. And along the way, of course, I knew we were going to be going over some very historical grounds, because these areas are where some of the first thermonuclear detonation and tests occurred. The first thermonuclear explosion was Ivy Mike, which deleted part of the atoll. So you see the pictures there. Essentially, if you go back, an atoll is essentially a coral ring. You once had a volcano with coral around the outside. The volcano's the size. What you're left with is a coral ring with a nice, aquatic center, a ring to almost surface level island, and then the ocean. And ID Mike deleted, eventually took a chunk out of the center of the stuff. It was actually a yield that was a bit more than what they expected. The one thing about the ID Mike's device was that it used, instead of tritium deuterium material, which is a solid, it used cryogenic deuterium and lithium. And so you see in that picture there on the left, the long vertical tank is essentially is the device. Those tubes coming out of it are essentially our testing analysis tubes. They were wanting to monitor, to do all kinds of measurements on the explosion, try to get as much telemetry out before the test equipment is destroyed. So most of that material you saw there is explosion analysis material. You see on the top on the top right, the island that basically got deleted. So that hole there is that island that was taken out of the chain. There are other chains there as well. There are other nuclear explosions. That concrete cap that's in sort of the top center is where the nuclear waste and the chemical waste is buried. Actually, it turns out most of the damage that was done to the coral reefs were done by DDT and other things. When the Navy left, or they were the last people there that left this island after the nuclear tests, there were rats that were left behind, and the rats basically multiplied like crazy. The guy that I talked to about that went back there, the biologist, said that the rats were so thick that essentially everywhere you stepped on a rat's carcass, right? That the rats had basically completely defoliated the place. The only reason why there's actually our plants left there is that natives, when they were, quote, evacuated trying to talk to another spot, they took with them their native plants, their native palms and the native plant materials. So when they came back, they brought back those plants. But it took a lot of chemical decontamination in order to be able to get the plant back to a livable condition. Ironically, it was the killing of the rats that did more biological damage than the nuclear explosion. Don't get me wrong. When Mighty Mike went off, 80 plants there were sort of burnt up. It was the reintroduction of stuff that created another ecological disaster.
Well, they tested that area quite a bit. I mean, they dropped like almost 50 bombs in that particular area, though, right?
Yes, and so you see other bombs are on there. So Google, if you go and do the Google Street View of that set, you'll essentially see I basically sat with my camera on the side of the plane going click, 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 and we basically did a camera run around the whole area. On the bottom, the one that's on the bottom slightly left, you'll see that the runway on the far end is kind of deleted. The ocean was sort of eating away the runway. The runway on the other side is kind of a different color. That's actually heavily reinforced concrete. That's where Mighty Mike was actually assembled. And so the airplane that we were landing on, we knew that the edge of the runway on the far side was kind of dodgy. So the idea was that we were going to land hot, that is, land flaps down where you're sort of barely touching, slowing down, and then toward the last moment, really put on the flaps and the brakes and slow down and stop here where it's reinforced, because it was not believed that the runway was probably too soft to hold the weight of the plane, whereas the edge of the thing was actually capable of holding planes. So we figured if they can assemble Mighty Mike there, they certainly can hold the weight of our plane. So as I say, it was, and standing on top of that dome, by the way, with a Geiger counter, you could barely detect radiation above background. I mean, I had to really try to say, yeah, it might be slightly above background radiation.
But that dome isn't going to last much longer, right? I mean, I heard that a lot of it's eroding to the sea, and
it is on a sand thing, and actually the bigger problem is essentially the chemical dump, right? That they went and scraped all the rat poison into the spot there, which is causing problems there. Now we swam in the bomb crater on the side, the small one there. I swam in that spot, and that's actually relatively uncontaminated. But again, it's
so you're more worried about the carcinogenic effects than the radiological effects.
Yeah, but actually, in flying over there, because the Gulfstream 5 flies at a fairly high altitude for efficiency, we were actually getting far more radiation levels up at
Yeah, isn't that weird? I mean, you get more radiation from a flight at 30,000 feet than you do from pretty much any of these exposures.
Yeah, and we were going at 42,000 plus. I mean, we were going at high altitude there, and it was and so that's where our radiation dosage came from, not from the standing on the cap of the waste pit.
Right.
Anyway, so on to this side.
And by the way, I just got curiosity. Did you just use a Geiger counter, or did you use any kind of neutron detector or alpha source detectors?
It was also a neutron detector as well.
Because those are much different to use. I've had to use all three many times.
Yeah. But I mean, we weren't there. In some ways, with the natives, we're kind of sensitive about this whole nuclear stuff. We didn't make it seem like we were scared of stuff or scaring them. But there's, the U.S. taxpayer has paid an enormous amount of reparations to the people out of Utah. But that's another story. We'll have another talk about the effects of nuclear weapons, and we can talk more about that in a month.
Yeah, but this is only part one, by the way. We might have a part two.
The potential.
By the way, just FYI, we're 20 minutes till 2-hour mark. So.
All right. Okay. So we're near the end here. So the potential nuclear material you use are U-235 or plutonium-239. Plutonium-239 is preferred because you can use them in implosion-type devices. You can use less material, and other elements are possible but not practical. So these are particular isotopes that could be used for bomb stuff. The problem is that they're either short-lived, right? So they would decay away, or they're and short-lived material also is radioactively hot. Remember, you want cold stuff to boost your yields. So while you could get americium there, you either need a lot of material, and it's also way too hot to be able to do anything practical with the device. So it turns out with the stuff that can go fuse, that you can make that sticks around long enough, it really is either U-235 or plutonium-239. There isn't any other practical alternatives.
Yeah, enriching. That's a lot of wattage for californium, and I didn't think it would be that 58 watts.
Yeah,
that's huge.
I mean, if you talk about back to the thing, where's my there?
Yeah,
yes.
I mean the heat. Yeah, californium 251. I mean, 58 watts per kilogram.
Yeah, but that's because you've got a half-life of.
Yeah, the shorter the half-life, you could have more energy released in a smaller period of time. So,
and also the type of decay products it has too is another thing that's there, because the neutron generation, it's not doing neutron stuff; it's doing other things that are going to be much more effective in heating. So enrichment, we talk about natural uranium is only about 0.72% of U-235. Is that the accepted numbers?
Yeah, somewhere in that ballpark.
Yeah, I guess it depends on which fuel you're using.
Yeah. But
reactor stuff is typically, I think, between about 3 and 4%.
Yeah, they're ours was somewhere in that ballpark. Very low compared to what you would find for
you can get as much as 5, but that's typically the type of thing. Mm-hmm. But highly enriched uranium is 20% or more, and weapons grade is 90 to 95%. Now, understand that weapons grade is making efficient weapons, but remember the first atomic bomb was only highly enriched. It wasn't weapons grade.
Yeah, and I think the highest they've supposedly have achieved is about 97%.
Yeah, it's possible. Waste product uranium, where most of U-235 is removed, is typically less than 0.7%, and there you're using that for things that basically a full class, like the uranium shells.
I wonder can anybody in the live chat tell us what they would use depleted uranium slugs like that for? See if anybody can guess that one.
So weapons grade designers, you can look at that to see there, prefer weapons grade plutonium at least about 93%, because the plutonium-239 plus a neutron makes plutonium-240, which is a fast fission rate. Actually, it typically has three or more neutrons when it splits. Then uranium-235 is 2 to 3. You can remove the effective isotopes, so you can make can be made from reactor grade plutonium. But again, weapons designers prefer that. It's not necessary because, again, the first bomb was only at 79% enriched. Again, you don't need much plutonium. The barosphere is actually relatively small, and the material needed for a ring is actually relatively small to get a nuclear device. And reactor grade plutonium is actually weapons usable. Is another thing that they're. But you could certainly turn it into weapons material if you want. But you've got to overcome the problem of neutron emission rates, and there's heat problems that also come from this situation. So the big problem is with non-proliferation, it's not hard to smuggle enough U-235 or plutonium-239 to make a bomb. You can carry enough. So here's a picture of a guy that suitcase he's holding is the plutonium that they used for the Trinity explosion. Remember, and the Trinity explosion was not an inefficient device. So if this guy can hand carry the plutonium needed for the Trinity test, and it's an inefficient device, you can imagine how small materials you need for stuff. The problem is that this much material is not very radioactive. I mean, kitty litter is more radioactive more easily detected than enough plutonium to make a bomb.
Well, it's got a long-term half-life too.
Yeah, so but you can tell the difference between kitty litter. But still, it's not a your standard batch detector in a simple case with plutonium is not going to detect the fact that you carried enough weapons grade plutonium in a case, in a hand case. And in fact, you look at the critical mass, right? This graph shows you the number of kilograms of uranium. That's that scale from 1 to 500 on one side, and the percentage of enrichment, right? And so you could see that dot out there at 93% has a low yield. But even when you're back to something like 80% enrichment, you're not having that much more material. Even if you're willing to do something that's probably 5 times the amount at 100 kilograms, you only need like 30% enrichment to create a device that can create lots of havoc. So hard part to make a nuclear bomb is making enough nuclear material. You need a Manhattan type project to build that. It's hard to hide. Making nuclear weapons efficient, reliable, and launchable is another problem, right? It's one thing to have a test, like a Trinity test, and say, yes, we could do it. It's another thing to make it reliable and make it small enough that you could do. Although far harder is for a government to make than a terrorist making sort of a crude bomb. That's one of the risks we run into. So designing and making a nuclear bomb, U.S. has done it, Russia has done it, France, China, Sweden almost did it. There's questions about whether or not India and Israel have that capability. That's debated, and I'll let you.
They don't. Israel has never recognized they even have nuclear weapons, if I'm not mistaken.
Yeah, that's why there's a question mark.
Not officially.
Yes, and we know from Sweden that they don't have it, although they developed the program to do it. So there's no secret to how to do it. I mean, the stuff I've told you in this talk has not disclosed it's in the secret. This is all well-known stuff.
Now, what happens if this talk was given in 1945 or something?
It'd be a different story. That'd be a different story. But there's lots of significant engineering challenges. So hard parts of making a crude nuclear bomb that, for example, even a terrorist group might have is obtaining enough weapons-grade material, processing the material in an appropriate form, the casting and machining of uranium, plutonium. Uranium is difficult. Plutonium is extremely difficult to work with, right? It's more and more radioactive. It's got all these weird crystalline states. It has all these brittle things, and if you don't do the right stuff, your metallurgy can go to pot. It is not a trivial thing to machine plutonium. So when you talk about creating a little sphere, there's a lot of stuff that goes into how to actually manufacture and make such a thing. And of course, building an explosive reactor in the pit is also very, very difficult. So implosion type weapons, the timing is hard. You have to crush the material, not just blast it. You have to recruit highly trained personnel, raise funds, and sustain an engineering effort over an extended period of time. And it's probably the most technically challenging attack ever tried to make a crude weapon. It's far more difficult to do something like that than the type of attacks, physical attacks that have been done by terrorists. Fortunately, that's the case. Now, short circuits can be they steal a device, or they're assisted by a state to give them the parts, or those are things that we worry about.
Purchasing a black market one.
Yes.
I mean, because when USSR fell, they lost track of a lot of nuclear weapons.
Yes. There was a lot of thermonuclear weapons, very effective nuclear weapons, that had some accounting problems. And they think they have accounted for nearly all of them, I think is what they would say.
Yeah, there's also a couple laying at the bottom of the seabed, but those are probably no longer viable because it's been so long.
Yeah.
But,
yeah. So other key technologies is things called Clytrons, which are things for doing precise detonations. That's stuff that you're not going to buy on eBay or learn about. Neutron generators and X-ray flash photography is something you need in order to do testing. So prior to actually doing the boom, you'll probably want to, and North Korea did the same thing, have chemical explosions to crush, blocks of aluminum or things to simulate plutonium. And you can't simply just go bang and look to see if you have some hardened pit, because the thing blows itself apart. You have to have very fast photography. And I'm not talking about Mythbuster type high-speed cameras. I'm talking about really exotic X-ray flash photography to understand what's going on, to understand the mistakes that are being made and how to correct and how to improve it. So these are key technologies, again, that we're not going to talk about, but they're there. So how do you make material? Well, plutonium, you need a reactor. So you take U-238 is plus a neutron plus neutrons produces plutonium. Whereas U-235 is an enrichment process where you're basically separating the two. An important thing to understand is that reprocessing is not the same as enrichment, right? If you're trying to concentrate to build more weapons grade uranium, that's a different thing than saying I've got nuclear fuel coming out of a reactor and I want to reprocess it. I don't know if Steve, you got into any of the reprocessing.
No, I mean, obviously in any kind of uranium reactor, you're going to have plutonium-239 produced in small amounts.
Yeah.
But we never bothered with the reprocessing.
Yeah. So, this U-235, U-238 keeps talking about, they're chemically indistinguishable, but they have a very slight difference in mass. One is rare and one is common. One is difficult to split and doesn't really chain react. The other requires fast neutrons in order to split. So essentially the process for a reactor is very, very different. So spent fuel reprocessing to produce plutonium is a different process than just enrichment. Typically, the two paths to get material is either you mine uranium, you put it in a reactor, you process it and convert it into material, or you take uranium and you enrich it and to fabricate the material.
Yeah, most of the time now they just add it. They use a mix oxide. It's uranium oxide and plutonium oxide, and they just mix it together in a fuel.
So enrichment typically is done in stages, where you have a unit that will, on one side, produce slightly more enriched material, and the other side, slightly less enriched material. So there might be a small amplifying effect where if you go through this process, the stuff that goes backwards is less enriched, the stuff that goes forward is slightly more enriched. And you have these stages. And typically, the type of thing for low enrichment uranium, you use a reactor. You need only a couple of stages, and you need only a couple of units, right? So the total number of stages might be, you might be 30. For a low enriched uranium, you need less than 10. And the number of units that you need, the number of machines per stage, also decays. But if you look at highly enriched uranium, it looks like this. So while this one might be 10 stages for producing reactor grade, highly enriched uranium requires 30 stages.
Each one refining it more and more and more.
More and more. But the one thing you find is that once you start enriching, it becomes easier and easier to limit to approach the 90% levels. And in fact, they use it by gaseous diffusion. Typically, the common thing is you have, the early one was by gas diffusion, right? The Manhattan Project, part of its big thing was at Oak Ridge, Tennessee, of using gas to diffuse across the barrier. So they took uranium, they bound it with fluorine, really nasty stuff, to create uranium hexafluoride. Mm-hmm. And the uranium hexafluoride would go across the barrier where the uranium-238 had more mass, and it would not go across the barrier as well as U-235. Slight difference in concentration. And they had many stages of the stuff that was pumped. And by the way, the development of things like Teflon. One of the reasons why Teflon was actually developed was for the Manhattan Project to handle fluorine compounds, because fluorine compounds are nasty, they react to almost anything, and Teflon's one of the few things that they can have coating metal, because otherwise the fluorine would just eat away metal.
Fluorine is more oxidative than actually oxygen.
Yes.
Yeah, it's a higher electronegativity.
Yeah. So, but modern stuff doesn't use that, because the thing like that Oak Ridge, Tennessee plant, Manhattan plant, while practical, it's very impractical. And at the time, they were using a non-trivial percentage of the entire U.S.'s power supply was going into this machine to enrich uranium. The modern way to do it is with ultracentrifuges. And essentially, you spin ultracentrifuging. You still make this uranium hexafluoride gas, but it requires about 20 times less power, and it's a small plant. A small building and a small power load is all you need in order to enrich uranium with centrifuges. And centrifuge refinement now dominates the world because the power plants like the Oak Ridge, Tennessee thing are just impractical. So one of the things that Kahn did was the black market a lot of the details of how to do this. He was a metallurgist, and that was probably one of his fortes and how he got access to some of this stuff. But they black marketed to countries like North Korea. When Libya turned over their stuff, they essentially turned over the same kind of design that we see in North Korea, because North Korea has let people go in and look at their enrichment plants, and what we see in Iran. So we know where the stuff came from. So is North Korea making high enriched uranium? Well, the answer is almost certainly they are. Centrifuge spins at a very high speed, excess of 50,000 RPM. And essentially they're using the U-238 is flung to the outer wall, and U-238 drifts towards the center. And they siphon it off against one of those stages where the stuff that goes out is slightly more depleted, and the stuff that stays behind is slightly more enriched. And so you have these stages, but they're very difficult to make. This has enormous forces with these things that are spinning around, even though they're relatively small diameter. There are normally forces. They're very easily unbalanced. They're very easy to explode going off center. And you need really excellent ball bearings at the bottom and magnetic bearings at the top. And sometimes at the bottom. And those technologies of how to spin something very fast was somewhat classified. Unfortunately, Kahn sold those secrets, so that now there's a few more countries, unfortunately, that know how to do this. Well, in fact, Iran's centrifuges, same kind of design, same type of process that we see that Libya turned over, that Iran has. The Iraq nuclear program was not at the point of doing this kind of enrichment yet. They were using plastron stuff, but Iraq was not nearly as far along as Iran has gotten, and obviously as North Korea has done, because they've actually.
How many more slides we got? Because I'd like to get some questions.
Just a few more questions. Okay. A few more slides. So, and here's one of the important points. Once you've enriched it from maybe up to like 4.5%, from the 0.7 the natural uranium that's 0.7% up to, let's say, 4.5%, you have done 3/4 of the work.
The initial part, the initial getting it to that is more difficult. After that, it's more efficient and it's easier to get to the higher enrichments.
Yeah. So having a stock of low enriched uranium for reactors could allow a country to reach high enriched uranium more quickly. And again, part of it is the fact that the plant that's necessary to make your reactor uranium can simply be kind of reconfigured, and it would be very difficult for you to detect that. And in fact, the kind of plant, the typical large, tech company office building is about the size of what you need and the power of a large data center, right? So it's not as if it's going to be obvious, screaming obvious, like a reactor will be. And the fact that a country might have today, like Iran, might have today a program to create reactor-grade uranium. Even if they promise not to cheat, it would be very easy for them to modify the design and extend it just a little bit with those little stages. Remember, again, when you look at the stages here, right? There is the 10 stages for low enriched uranium were the number of units, and that's the thing for high enriched uranium. So the point here is that it's very easy if you have the low enrichment process to cheat, and it's very difficult to detect that you've cheated in that process. So, Iran had centrifuges designed for about 20 years, right? So they've been trying for about 20 years to do it, we know. And Khan gave them basically the technology talk and some other items based on what he sold to Libya. And this particular thing, it was difficult for them. They had to overcome some significant engineering challenges. Certainly Khan helped them do that, and they had been practicing for about 20 years. So they essentially mastered it. Clearly the North Koreans also mastered it as well. So it's how difficult it is to make it. Well, United States and UK developed simple but good enough centrifuges in a few years with a few people. They took a while to do it, but Iran has done it. And you can debate whether or not they have only low enriched uranium or they just have essentially a set of spigots. The inspection process has shown that they're not has not detected that they've been building highly enriched uranium. However, the evidence is that they tried or they tested it. And the centrifugal plants are easy to hide. Here is, in fact, was North Korea's enrichment plant, that sort of that blue building. We didn't know it was there until they actually detonated the reverse device, and then they brought the U.S. to the spot and had people go through it and showed it, so we actually discovered what that building was. Now, by the way, it turns out they're building a second building along the side, so it seems like North Korea is actually trying to improve and accelerate their enrichment process. Producing plutonium is harder because you have to have a reactor, spent fuel, the radioisotopes, they show up very well on satellites, and so those are easy to detect. So the plutonium production, in fact, North Korea published their schematics for some of this stuff, for their reactor. This particular reactor design was not really meant to generate power. They do get some power of it. They're more trying to remove heat from the reactor core because they're trying to cook uranium and turn them into plutonium. So, this is a fascinating thing because reactor design people looked at this and said, that's a weird reactor design. And what realized was, oh, this is actually not for power plant production. This is for plutonium.
Yeah, and it's graphite moderated too.
Yeah.
Which is not a great design.
No.
Yeah,
but
graphite has what's called a positive coefficient of reactivity. Those kinds of reactors, you actually have to work to keep them from going out of control.
Okay.
That's a bad design. You want something that you don't have to fight to keep it going. You want something you want something that you have to fight to actually keep going, rather than fight not to have it to be supercritical. So that's a very bad design.
So the North Korean reprocessing plant is easy to see. The radiation leaks from that sort of thing, so we can detect it. So the uranium enrichment is hard, it's easy to hide. And if you're doing it for power plants, it's very easy for you to reconfigure it quickly to boost it. Plutonium is a harder thing to do. But remember, plutonium is the one you want to do if you want to do efficient bombs. So we know where the North Korean reactor is that's doing reprocessing. So could, that one of the things also to kind of understand, again, is that civilian power plants, that some of the enrichment technology to create nuclear fuel is critical, but the actual civilian itself does not get you very close to a bomb. Having a nuclear reactor does not give you close to a bomb. Having the ability to take fuel and reprocess it can produce something, but it's obvious if you're doing it. Having a uranium enrichment process by centrifuge is easy to hide, and that's where probably the biggest problem with proliferation is. So, there certainly are proliferation issues in terms of if you have a nuclear power plant of where your fuel is coming from. It's why oftentimes members of the nuclear club do the enrichment for another country and give them enriched material rather than encourage the country to enrich themselves. I thank you very much for taking the time there. I certainly want to give credits to Dr. Matthew Bon, who has 2 very excellent YouTube videos. He goes into a lot more technical details about how actually bombs work. And he's a person that's done a lot of work in non-proliferation. There's also a couple of actual, surprisingly factual Wikipedia sources that this material came from. And certainly want to give credit to part of this lecture to Dr. Martin Bond, some of those images I took from his lecture, and certainly is a good source of non-classified material for this stuff. So, any questions?
Well, let's find out here. Go ahead and stop screen sharing. I'll go back to our main layout here in a second.
Stop screen share.
Okay. We do have one question right off the bat, but but it was more of a technical question, so I was saving it to the end, and then if people want to ask after that, we'll get some in. But the person had asked Landon, is there a fundamental relationship between mass and charge? How is an electron able to produce an equal but opposite charge to the proton with far less mass?
Well, the mass-charge ratio of an electron is very different than the mass-charge ratio of a proton or a neutron, which has 2 charges inside of it. So they're fundamentally different particles. One is a baryon, one's a lepton. So one is the proton is made of things called quarks that gets its charges from the combination of the 3 quarks. The electron is a charge in and of itself, and it's a lepton. It's a fundamentally different type of particle that reacts fundamentally different. So it's not really correct to say that a proton is an opposite of electron. They have fundamentally different masses. They're made of fundamentally different processes. An electron, you don't have to have the strong nuclear force to keep an electron. It just is, right? It's electrons. It's just an electron, right? That's whereas
they're indivisible.
Proton requires weak nuclear force as far as decay stuff. If it decays, you've got an atom involved in decay, and strong nuclear forces to keep nucleons together. So they're very fundamentally different beasts. Yeah,
it's a hard thing to wrap your head around a partial charge, and I'm not talking like a partial charge like on DNA. I'm talking about the actual quarks themselves have non-integers for charges. So like a proton would have plus 2/3, and then what is it, minus 1/3. So I mean, that gives it an overall net charge. But a neutron would have like plus 2/3, minus 1/3, minus 1/3. So your overall is 0. Those are hard things for people to wrap their head around because you're used to saying, okay, either it's positive or negative, but no, quarks don't have full charges. So
yeah, so again, it's fundamentally different.
They're not indivisible like that.
And by the way, there are actually you talk about the leptons. Mm-hmm. There is also a tau and a mu that are also.
And so electron neutrino, tau neutrino, and a mu neutrino, isn't it?
And because of that, there's an electron, tau particle, and a muon.
Yeah.
And those are negatively charged.
I remember something. I'm
excellent. You did right. And they're negatively charged, but they have fundamentally different masses.
Right.
Even the quarks inside of
tau's the heaviest out of all of them.
Yeah, have different masses as well. And this is based on what we observed, what we measured, as well as fitting a standard model.
All right. So what other questions we got, real quick? Let's see here. Anybody? Is cold fusion possible? I'm going to throw this out there. I'm just going to say no. Everything I've looked in with cold fusion was all just an exothermic reaction, but it was all chemical. There was no real net energy released from the amount of energy going into the system. What do you think?
The Pond-Fleischmann claims were at best a misunderstanding of the experimental results. I don't know of a way to do cold fusion. I mean, fusion, you've got to get the particles in close enough, overcome the repulsion, charge repulsion, in order for quantum mechanics to take over and for them to merge. And there doesn't seem, I don't understand how you would get a chemical reaction or some other, other than an extremely difficult thing like a crushing from lasers or a pumping of a plasma or a Z-pinch, magnetic collapse, some very extreme exotic conditions in order to have fusion occur. I don't know how you would do that in a chemical low energy environment. You can argue that the energy necessary to bring stuff together to get them to fuse, that's going to require pressures and temperatures, and doing it cold is kind of anathema to the whole thing.
Convert me out.
So I don't think it's possible.
Yeah, I don't think it's possible.
I would be surprised if it's possible. I'm not going to say it's impossible, but I would be surprised if it's possible.
Does MOX fuel play any role in weaponizing? Does it free up other fuels for making weapons? MOX fuel is generally used for commercial use, but it can be used for weapon grade. But if you're going to be, for example, when you re-core something, or if you're going to be putting in a MOX type fuel to a reactor system, that's a completely different kind of license. So
yes,
it's a whole ball game.
If you're pulling out plutonium out of a reactor that's been spent fuel, the reprocessing process is one thing to get to return back some of your reactor uranium in order to be able to go forward. But that plutonium that's left over has to be refined, and the refinement process and metallurgic process for plutonium is extremely difficult.
But the fuel for the MOX doesn't come from a reprocessing, if I remember. I thought for a MOX it's actually just introduced, but it's not coming from a reprocessed type plant.
Oh, I thought you were talking about reprocessing. I'm sorry.
Yeah, because I'm pretty sure that you can get 239 from reprocessing, but the way MOX fuel uses it gets 239 and puts it in a mixture between uranium oxide and plutonium oxide, and then it gets reintroduced to existing reactors to create efficiency. Yeah. In that
particular case, because you're not having to refine, right. You don't have to do plutonium metallurgy, but you're talking about going from MOX to weapons grade.
Yeah, it can be done, but I don't think they use it for weapons grade. But theoretically, I guess it could be right.
But it's difficult, and furthermore, getting the plutonium is just a small process. It's machining it and turning it into something usable. That's a non-trivial thing.
Prepper ask. Oh, by the way, thank you, Prepper, for soon becoming a Patreon. Anybody else wants to become Patreon? Please let it.
Thank you.
I appreciate it. Anything on this channel. This main channel is literally what I live off of, because I haven't got a dime yet from Non Sequitur.
Yeah.
We haven't done anything with those funds, so I am literally living off this channel. But Prepper says, would it be possible that an X-class solar flare generating a strong enough EMP could set off a nuclear weapon, or are they sufficiently shielded enough? There's a lot of... the thing is that even if it trigger... Well... I think he's asking, like, can the EMP cause a triggering scenario? Because the EMP itself is not going to cause a weapon to explode. But X-class solar flares don't really produce a lot of energy from our point of view. I mean, from the sun, yes, but I mean, it might blow up a transformer, right? I mean, it might have some kind of induced effect, because you're having these charged particles and magnetic fields going across these lines, and that's going to induce a current. But I'm pretty sure that they're pretty well shielded. Yeah. I don't think an X-class flare is going to take.
Well, I think the other thing as well is that when you talk about an X-class solar flare, you're talking about something that might be on the order of 1/10 of a milliwatt per square meter of energy. It's not at Earth's distance. It's not.
Yeah, and it's over a square. It's over a square. It's over the entire Earth, right? That it's hitting it. So it's not really a lot of energy if you think about it. That's hitting the Earth now, is it?
So you're talking about those thermonuclear devices. You're having an atom bomb right next to it. That's the type of X-ray fluxes you need. Not.
Yeah. Well, I think it's talking more like an accidental triggering.
Yeah, and so not a.
No.
And so the other thing is you say is, well, okay, could some event, external event, even a lightning strike and so forth, set off a bomb? Well, the bomb designers are rightly enough, are extremely careful in their designs, because you do not want your bombs just aging and going off, or you get a computer virus bug on something and it says go bang. The amount of effort it takes to actually take a actual nuclear warhead and cause it to detonate is extraordinary in terms of what has to happen. And it's difficult to do it when you want to do it. The processes that are there, it's in a form, and again, it's why we don't use gun-type bombs. The problem is a gun-type bomb, if the black powder decays or something hits the wrong way and the conventional explosive goes off,
you're screwed.
You're toast, right? That's why implosion-type stuff are used instead, and no one is at this point insane enough to do a gun-type bomb.
I mean, older weapons, sure. Like I have to agree with the cannon type. Then you might theoretically have these problems, but in newer weapons, it's not a concern. Yeah.
Now you say, well, couldn't terrorists build a gun-type bomb? Yes, but they'd have to get hold of enough gun-type enriched uranium to do that, and that's a difficult process. It's getting all the material, that much material is there, because in a nuclear reactor, how much uranium-235 might you have? What would be the total mass you would guess?
How many kilograms?
Yeah,
it's not an exceptional amount. I don't even remember. It's not a lot. I mean, like I said, the entire reactor core itself is about the size of a standard trash can. I mean, it's not that big. So you can.
So even if you grab all the fuel out of a typical that type of nuclear reactor, you don't have it in the right form. You don't have enough material to do it, and people would notice, when the nuclear power generation shut off. Like, hey, what happened to our plant? And so even if you took that, you would then have to enrich it, right? And
you would never get enough fissile material from a nuclear reactor. And plus, it's, like I said, it's the way it's configured in these pellets. You'd probably end up dying trying to take it out. I mean, it's not an efficient way to get uranium, I assure you.
The other thing I understand is that nuclear reactors are designed such a way that you have to have exert a lot of effort to keep the reaction going. Mm-hmm. That's the design. They're not like the bomb where it's sitting there just short of criticality, and you do something and it becomes supercritical.
Yeah, pressurized water reactors especially, because they have a negative temperature coefficient of reactivity. That literally means as the reactor gets hotter, as the moderator gets warmer, it gets less dense and it becomes less efficient, which means that you have to actually try to keep the criticality going. The reactor's trying to shut itself down. It's trying to stop being critical as it goes on. So you seriously have to keep the reaction going, and that's a fail-safe design. You don't want it to be the opposite. So
and then even if you try to trick it into that, trick it to pull out all the control rods,
you wouldn't. You would have a steam explosion, but that's it.
Because again, remember, it's not just you have enough critical mass material together. Because if you were to pile it together, it's going to blow itself apart. You can have an explosion, right?
You would have a control. Well, that's happened once with the Army reactor. The SL1 they had 3 control rods, and one of them, the person was pulling it out. They were only supposed to raise it a few centimeters, and it was manually lifted out. And he lifted it up quite a bit more, added a bunch of reactivity to the core, and it actually caused a flash of the water into steam, and it just ejected the core, the actual control rod, stuck him to the ceiling, killing him instantly.
Yeah.
So it's dangerous.
But I don't know if that answered the person's question, but you couldn't have a solar flare bump or electrical discharge, or even, you couldn't even, have some thing of lining a bunch of explosives around the chamber to try to implode it. No, it's not gonna work. It's the configuration inside these devices are very, very different at very high densities compared with what you could get even if you had enough material in a reactor to make something, reprocess it to a bomb.
All right, so we're probably going to wrap it up. I don't see any other more questions. This was our second edition. Next week, we actually have possibly an astrophysicist coming on.
Excellent.
We're going to see how that goes. And then I think, do you have a part 2 to this presentation?
Yeah, well, we can talk about sort of, this would be another talk we can do later on when people have wrapped their heads around this sort of thing.
I would like to eventually have a detailed talk about a little more the physics. I mean, I would like to get into the relativistic effects of the things taken into account, like even the energy mass relationship. There's a lot of relativistic effects that can be taking place because of the orbitals, and I like to get into orbital mechanics. I like to get into talking about what happens when you get higher on the periodic chart with the relativistic effects of the electrons. And there's some weird things that happen. It's really cool stuff. And so maybe we can do a presentation.
Yeah, pun intended. But the other thing I say, the other part of it, you see, is part 2, is talking about the nuclear blasts and what happens when you have a detonation. The effects of that is sort of the second part of the talk on. So again, I hope this gives you a little bit more information about the issues of nuclear weapons, the non-proliferation issues, and what we're facing when we're trying to keep these weapons under control. You certainly didn't learn enough to build a bomb there, because essentially there's some critical details left out of the talk. The purpose of this talk was to give you a notion about what the technology is like and where it's difficult, where it's not. It's important to understand that the processing of nuclear power is fundamentally different than the processing for building a nuclear bomb. Unfortunately, some of the information is critical information on how to build and how to enrich your fuel is getting out, and unfortunately, the odds that some idiots on a suicide can build a crude bomb are increasing, and that's the thing that Russian people are most worried about.
Yeah, somebody in the live chat said that the guy on the SL-1 lasted for 3 days. I don't remember that particular thing. When we had to study this particular accident, I thought he was killed on contact because it basically hit him midsection, stuck him on the top, and it was about 1,000 rem on contact. Now, 1,000 rem will kill you over a period of time, but it's going to take several days, but you will die. 1,000 rem is 100% chance you will die. About 400 to 500 400 to 500 rem, you have about 50 chance, but 1,000 rem, you ain't going to survive that. But I don't know how he lasted 3 days up there. Somebody said according to the wiki article, but when I learned it, he died instantly, but who knows, right?
It might be. I mean, certainly he wouldn't have been able to live very long.
He wouldn't have been in good shape.
Yeah. The other thing I'm going to say in terms of the two hot points for nuclear weapons in the world, in terms of North Korea, they certainly have achieved boosted, smaller, more efficient atomic weapons. And there is credible evidence that they're trying thermonuclear. They may not have gotten a very good yield, but that they're in that early stages. In the case of Iran, they have a nuclear enrichment process, which is capable of building highly enriched uranium and weapons-grade uranium. It is very easy for them, should they choose to not abide by the agreement, to reconfigure and rapidly move towards the development of even a crude nuclear weapon. And people...
It's a frightening thought. It really is.
Yeah. And so I'm not going to comment on, leave it for the policymakers as to what to do about that. But again, it's very easy for Iran to decide not to abide by the agreement or to cheat. It's very difficult to catch them. And the time to go from I'm enriching uranium for my reactors to I'm going to build a bomb, or going to build enough material for a bomb, is a relatively short period. The question is whether we also have an idea about other stuff that Khan gave them. We know that Khan's leak to the North Koreans gave them a nuclear device. So it is not inconceivable that the same stuff that Khan gave to Iran could allow Iran to build a nuclear device. We know from Libya what they turned over. They certainly had the program necessary to do a nuclear testing. So we'll have to see on what's going on there.
Was there anything else you want to plug before we take off? Like your shirt, maybe?
Oh yeah, actually, some points. This is a I Am Unforgiven. This is from the Milwaukee Atheists T-shirt thing. They have a T-shirt collection there right now. I believe I know that of course, that this is if you become a $10 a month Patreon, you can be entered into a T-shirt drawing. Or you can buy it off of them. Check out Milwaukee Atheists for that thing. But there is you be one of the cool people to have this particular T-shirt.
Yeah, and you might notice somebody else wearing it as well. He goes by the name of Aaron Ra. So I think he has one. But anyways, Landon, thank you very much as usual for bringing your exceptional brilliance and your presentation.
Thank you kindly.
I'm hoping that people got something out of it. Again, this was a very, very just brief overview of these topics. They get a lot more complicated, I assure you. But I think that most people got some takeaway from it. If you have specific questions, just ask in the comment section after this uploads, and we'll see about kind of getting to those questions afterwards. But let us know what you think of it. Like this video if you liked it, and subscribe. And if you want to become a patron, I do appreciate it. Every little bit helps. But we're going to be doing this every Sunday now when Landon is available. If not, I'll get some other co-hosts. But right now, he's kind of my primary one. So if you
I'm here about available about every other week.
Like bi-weekly, I think, for him. And I got some other people on the side. I got side people, you know.
He has connections.
I got connections. So we're going to put on a show every Sunday, DEFCON 1 Science. And thank you all for watching.
Thanks.